which is correct. And from there, we follow a series of logical steps, which have to be correct, obviously, until we get to the final statement or the final proof that we want to show. As I said, in Pure 1, it's not too difficult. What you want to do is just make sure that you covered all the bases during the steps and you're basically following mathematical steps which are correct. So let's go ahead and look at some proofs. So we have this term and we want to show that it's always negative. Now in this kind of case, you have to think to yourself, how do I show that it's always going to be a negative term? Well, we ideally want them to have minus signs, right? That way it's going to show us that they're negative. So what we can do now is I'm going to now take negative out and I'm going to say it's negative n squared plus 2n plus 3. Now this middle, the term in the bracket, what I can do next is complete the square. You'll see why. When I complete the square, I get minus, and then we have n plus 1 squared minus 1 squared plus 3, which will reduce to minus n plus 1 squared plus 2. Now if I multiply out the bracket, I get minus n plus 1 squared minus 2. Now this we can now state that is always going to be a negative term. The reason being is because for any n value I put in, it's going to be n plus 1 all squared. So if I put in like a negative value, because of the fact I'm squaring it, it's always going to be a positive value. However, we have this negative sign in front of it, which will now turn it into a negative value. Furthermore, we have this minus 2 as well, which will further make it more negative. So you can see that this term is going to be negative, this minus 2 is going to make it more negative. So for any n value, we can say that this whole expression is always going to be negative. Right, let's look at another example. Now in this case here, what you should notice is these like equal signs, but there's actually 3 horizontal lines rather than 2 that we're used to. The 2 that we're used to actually stands for equals, which means that we can like shift the left and right. We can like subtract and multiply and divide it as we normally did. When we have dealt with 3 horizontal lines, this stands for equivalent. And what that means is we can't shift left and right. It tells us that this term here, or this expression, is equal to or is this term here, meaning we can't shift left and right. What we do instead is we use one side, manipulate it to make it into the same form as the other side. So let's go ahead and do it. So let's start off with the left-hand side. So I'm going to say left-hand side is equal to x plus root y, x minus root y. The next logical step is expand or multiply out the bracket. So we get x squared plus x root y minus x root y minus y. These 2 middle terms will now cancel, leaving us with x squared minus y, which is equal to the right-hand side. This is an example of a proof. Now we have to deal with proofs in a lot more detail when we look at trigonometric functions, so keep your eyes out for that. But when we're dealing with mathematical proofs, just be aware that when you're dealt with this equivalent sign, you can't shift left and right, you can only look at one side. You could start off with the right-hand side and try and make it to the left-hand side, but it's a bit more difficult in most cases, so I would recommend starting off with the left-hand side. The final example I'm going to go through is this one here. And they're saying that these 3 vertices is the vertices of a right angle triangle and show there's a right angle triangle. When dealing with this question, you have to understand what we're trying to do. It's a right angle triangle, and we have to understand the characteristics of a right angle triangle. Well, we know that it's 90 degrees, and we also know that you can use Pythagoras, right? We can say that a squared plus b squared is equal to c squared. So using those characteristics, that's how we're going to go ahead and prove this particular question. So let's look at the perpendicular one first. So we can say if we find the gradients of each one, hopefully if we multiply them together, we should get minus 1 for a combination. So if I find the gradient of AB, I get minus 1 over 2. If I find the gradient of AC, I get 3. If I find the gradient of BC, I actually get 2. So you can see that the gradient of AB and the gradient of BC, if you multiply them together, we get negative 1, meaning that those 2 lines will be perpendicular. We can now prove, or let's now show that they satisfy Pythagoras. So the length of AB is root 5, the length of AC comes up to root 10, and the length of BC comes up to root 5. So if I do root 5 squared plus root 5 squared, it comes out to be root 10 squared. So that satisfies Pythagoras. So you can see with this proof that it's just basically make your initial statement, follow the logical steps, and then make your final statement concluding the proof.